Hey guys, sorry this is coming out late. In order to kind of make up for that, I'll make sure that the quiz is due on Sunday at the end of the day instead of Friday by the end of the day. I also should have the next week's lecture already up either by today or tomorrow. I'll be on vacation in Orlando tomorrow till Monday. I'll still be reachable if you have any questions, of course. I just want to make sure y'all have that in advance instead of having to wait until Tuesday for yet another lecture. All right, so we did all the crap about methods, ethics, all that really exciting, fun stuff. Let's go back to the fundamentals, okay? So, whether it be a coin flip or a random sample of your data, you really can never predict the results of something in advance. Um, with these random events, it always varies, whether it varies across multiple coin tosses or multiple samples. However, there's an eventual predictable pattern in the collection of results. It's one we find after many, many repetitions. So this really is the basis for that idea of probability. I know that's a lot of like flowery language and jargon and crap. So let's actually do an example. So let's flip a quarter. Let's just assume that I'm flipping a quarter. My first flip is heads. My second flip also is heads. My third flip's tails. My fourth flip's heads. My fifth flip is tails. Does that mean that there's a 60% chance of getting heads with this coin? Does that mean that the coin's broken and it's no longer 50-50? No, all that means is we don't have enough data to actually get to the truth yet. We need to do more replications. We need to do more samples. So what if we do 5,000? So you can see from the textbook, somebody did just that. You can see as with both of these trials, so the red one and the dotted blue one are two completely different trials. You can see one starts really high with a lot of heads and eventually starts tapering off. And this other one, you see a lot more variability. It goes back and forth, but both of them eventually taper off at what the truth is, 50-50. We know that if the coin is manufactured correctly, there should be a half and half chance that it's heads or tails. So as we approach infinity, in other words, we do more and more trials, the probability is going to approach its true number. So the probability, of course, of getting heads is 0.5. It says in the book, like there's these experiments that's apparently some South African guy who was a statistician got captured in World War II. And in one of the prison camps, he had a coin and he flipped the coin like 4,000 times. And he ended up getting like 50.24% heads. So you see, even with about 4,000 trials, it's not exactly, but it's close enough. So what is random? So of course, when we talk about our normal life, random means something's unpredictable, right? We never know what's going to happen. It's completely just up in the blue, whether it's going to be this or that. The statistical definition of random is similar, but there's some important distinctions here. First, the individual events have no statistical pattern, but the overall pattern is going to emerge in the long run. So, coin tosses, that's a big example of random. It's impossible to predict a single coin toss. I mean, you can guess, but you can't predict with any degree of correctness over the long term. But we do know that after a long enough coin toss, the true odds are going to come out. It's going to be 50-50. And so that's the idea. Statistics, we don't focus on single events. We focus on patterns of behavior. We don't just flip the coin once or 3 times or 5 times. We flip it 5,000 times. And that's how we get where we're closer to the true average. Okay, so some more definitions. First off, independent. Basically, when we talk about independent trials or independent events in statistics, it means that the outcome of one trial doesn't influence the probability of the outcome of any other. So basically that means if you do one trial, does that make the same or different results more or less likely? Think about flipping a coin, right? If you flip a coin heads, that doesn't mean that the next time you flip a coin, either heads or tails is more likely. The odds always stay half-half. An example of a dependent event is, let's say we get a bag of Skittles, right? And we pour it out. Let's assume all the colors are equal. We pick out a purple, and we eat the purple. Well, now we are less likely to pull out another purple in the future. The outcome of the first trial, where we pulled a purple, influenced the probability of the outcome of our next trial, because now purple is less likely for a Skittle to be pulled. We'll have some more examples of that in just a second. Then, of course, lastly, empirical. You see a lot of things like empirical evidence. Basically, what that means is it's found through experiments. So, let's talk about whether or not some things are independent. When we're asking whether or not events or trials are independent, always ask yourself, does the outcome of the first event affect the probability of the second event? So flipping coin. Well, like we just said, flipping a coin is an independent event. If we get heads, that doesn't change the odds of the next trial. We're still half-half likely to get either heads or tails. Same thing with this, right? Let's say we choose 2 cards from a deck. We get an ace of spades and a 2 of spades. If we put them back, we are now just as likely, 1 in 52, likely to pull those cards again. How about choosing 2 cards from a deck without replacement? Well, in that case, that would be a dependent event. If we don't put those cards back in the deck, the odds of pulling them out is 0. So in that case, that would be a dependent event. What about winning in roulette twice in a row? Well, ask a gambler and they would say it's a dependent event because, you can get on a roll and you're more likely to win if you start winning. But statistically, winning in roulette twice in a row is an independent event. Whether or not you win on the first event doesn't change whether or not you win, the probability of you winning on the second event. I like this last one because it's kind of tricky. Winning the lottery multiple times. So, if you don't win the lottery, are you more or less likely to win it again? Well, it depends. Probably you are. If you don't win it the first time, you're probably less likely to win it to the second time. Sure, I haven't won it both times because I'm one of the people that don't buy lottery tickets. So I have a 0% chance of winning the first time and the second time. So you can only, people who win the first time, they're the ones who buy the lottery tickets. So they're vastly more likely to win the second time. I mean, the odds are still terrible, right? But you are still more likely. So that would be a dependent event because the outcome of the first event, you winning or not winning the lottery, affects the probability of the second. If you win the lottery, you're more likely to win the lottery again because you're part of the people that buy lottery tickets. All right, so probability models. That's a big fancy word, and I'm throwing a lot of jargon at you, but we'll get through this. So a probability model is a description of a random phenomenon in the language of mathematics. It's a big fancy complicated way of saying we lay out the outcomes of an event and the probabilities of those outcomes. So oftentimes when we talk about probability models, we talk about sample spaces. The mathematical symbol of a sample space is a little s, or a big S, I guess I should say. Basically, it means the set of all possible outcomes. Looks a lot more complicated than it is. So the format is S equals, and that little weird brackety thing, I forgot what the specific term for it is. I call it the thing you do when you hit shift bracket on your computer keyboard. And then what you'll do is put in the all possible outcomes and separate each of them by commas. That sounds nonsensical, but let's look at a couple examples and it's going to make a lot more sense. So let's say we flip a coin once. Our sample space, all of our possible outcomes, is heads or tails, right? Those are our only two outcomes. What if we flip a coin 3 times? Well, we've got a lot more options, right? Heads, heads, heads. Heads, heads, tails. Heads, tails, heads. Heads, tails, tails. Tails, heads, heads, etc., etc. So those are all possible outcomes. And of course, even though, tails, tails, heads, and heads, tails, tails is kind of the same, all we care about is the sequence. So we're going to write all of these down. The next one, the number of heads when you flip a coin 3 times. Well, let's look through it, right? We have heads, 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 so that's 3. Heads, heads, tails, so that's 2. Also 2. 1, 2, 1, 1, and 0. So our options in order are 0 heads, 1 head, 2 heads, and 3 heads. So instead of having to write down that full complicated thing, we just write down the number of heads that we're possibly going to get. And of course, the other one, rolling a die once. Well, our options are the options on the side of the die, right? It's 1 through 6. Those are our only possible options. So we use the word event, so let me define an event. An event is an outcome or a set of outcomes of a random phenomenon. An event is basically what a subset or a subgroup of the total sample space. So let me go back one slide. So flipping a coin once, there are 2 events here, right? There's the heads event and the tails event. So that's 2 events. Here we see 1, 2, 3, 4, 5, 6, 7, 8 events. So those are our 8 possible events. These are our 4 events right here. And then these are our 6 events right here. So that basically all an event is just a subgroup. Individual events, we can talk about them as well. And then also group events as well. All right, so the basic 4 rules. Before we discuss, remember when we talk about probability, we're talking about numbers between 0 and 1. Sometimes it'll ask you to have it in a decimal form. Sometimes it'll ask you to be in a percentage form. So when you think about these numbers, it really helps to multiply them and think about them as percentages. So obviously 0 is 0%, 0.5 is 50%, and 1 is 100%. So I'm going to give you the definition of each rule, kind of the mathematical notation, how they talk about it in mathematics of statistics, and my explanation kind of using an example at the end. So if you don't get it the first time around, just wait for the example, and hopefully we should be able to get it. And of course, if you don't get any of this, feel free to text me, message me on Google Classroom, email me, the usual. So rule 1, that is kind of obvious. Any probability is a number between 0 and 1. So our mathematical notation, the probability P of A of any event A satisfies 0 is less than or equal to P of A, which is less than or equal to 1. Basically, all this means is any probability is between 0% and 100%. Can't have under 0%, can't have above 100%. It's kind of an obvious rule, but yeah. Rule 2, all possible outcomes together must have probability 1. Our mathematical notation there, if S is the sample space in a probability model, then the probability of the entire sample space is 1. This makes sense, right? The probability of all possible events are going to add up to 100%. You're never going to have a situation where your total's 80%. Something's gone terribly wrong then. So at that point, redo your math and figure out what's happened there. So, because it's always going to add up to 100%, right? Because there's, 100%, it's your total choice of options is always going to be 100%. All right, rule 3. If 2 events have no outcomes in common, the probability that one or the other occurs is the sum of their individual probabilities. So the mathematical notation version of this is two events, A and B, are disjoint. Don't worry about disjoint, we're going to talk about it in a second. If they have no outcomes in common, and so can never occur together. If A and B are disjoint, the probability of A or B happening is the probability of A plus the probability of B. So basically, something being disjoint doesn't mean that it's dependent or independent. It's something completely different. All it means is that it's mutually exclusive. You can only be one or the other. You can only be a certain age, right? You can only be 11, 12, 13, 14, 15. So you can only be a junior, senior, freshman, sophomore. These are very specific categories where you can't be in multiple ones at the same time. You'll also see this referred to as the addition rule for disjoint events. Rule 4, the definition is the probability that an event does not occur is 1 minus the probability that an event does occur. So the mathematical notation of this is basically called the complement of the event. So the complement of an event A is written as A of C, or A to the cth, or yeah, A subscript C. P of A subscript C equals 1 minus probability of A, right? So let's think about, well, let's make it simple. Coin flip, right? Well, the probability of heads is 0.5. The probability of tails, well, if we don't know that the probability of tails is also a half, we can just go 1 minus 0.5, and that gets us 0.5. Or let's think about the probability of a die, right? The probability of rolling a 1 on the die is 1 in 6. So the probability of not rolling a die would be 1 minus 1/6, or 5/6, or whatever however that comes out in decimals. I'm just doing that off the top of my head. Yes, so anytime you're talking about the probability of something not happening, you also see that referred to as the probability of failure, then it would just be 1 minus the regular probability. So this is also called the complement rule. So let's give an example. Brent University. So in Brent University, there are freshmen, sophomores, juniors, and seniors. Brent University has 100 students, 27 freshmen, 24 sophomores, 20 juniors, and 29 seniors. So, rule 1. The probability of being any one category is between 0 and 1. So the probability of us picking a random person and for them to be a senior would be 0.29, or 29%. Rule 2, they've all got to add up to 100%. So if we add them all together, the probabilities, probability of being a freshman, 0.27, probability of being a sophomore, 0.24, probability of being a junior, 0.2, and probability of being a senior, 0.29, that equals 1. Rule 3. So obviously your year that you're in is a disjoint event. You can't be a freshman and a junior. So in this case, we can find the probability of a random student being a freshman or a sophomore by adding 0.27 and 0.24. And then we get 0.51, or 51%. Then lastly, rule 4, if we wanted to see the probability of a random student not being a senior, we would just take 1 minus 0.29, and then that would give us 0.61, or 61%. All right, so next we're talking about equally likely outcomes. So this is kind of complicated to explain, but it makes sense, like, obvious, or it makes sense kind of when you kind of process it. So in any situation where all possibilities are equally likely, so the probability of an event happening is the reciprocal. So basically the reciprocal is you take the number, and you put it in the denominator and 1 in the numerator. So you think about a coin flip, there are 2 options. Both are equally likely. And of course, the probability of heads is 1 over 2. In a six-sided dice, there's 6 options, all equally likely. That means the odds of any one dice result, 1 over 6. All right, so rule 3, I already talked about those OR events, right? Where we have the probability of being a junior or a senior, of being a freshman or a sophomore. So in that case, both are disjoint. So what about if we want to know about AND events, where specific events occur together? So let's use what we call the multiplication rule. So you can see here, I wrote it out as rule 3, the OR events right here. So OR events. So what are the odds that we roll a 3 or a 2 on the dice? So obviously those are disjoint, so we just add them together. So probability of getting a 2 or a 3, 1/6 plus 1/6. We get 2/6, or about 33%. So we got to do AND events. What are the odds that we roll a 3 and then a 2? So we would not add here, we would multiply, because the odds of getting a 2 is 1 in 6. And the odds of getting a 3 after that is 1 in 6. So we would multiply those together. So that would be 1/36, or around 3%. So yeah, anytime you're doing AND, if you flip a coin and you get a heads and a heads, that would be a half times a half and would equal 1/4. Cool, so that's it for this one. Like I said, I'll be putting up the other lecture sometime soon for next week, just so you can get a head start on it, and because I'll be gone Monday. Yeah, talk to you guys later.